Thanks for your attendance. Hello, everyone. Today, my topic is about Kata Containers performance evaluation and optimization on Arm64. Firstly, I will give you a brief introduction of design architecture. Secondly, I will give you the status update on Arm64 for Kata Container. So if you have used the Docker container, you might think about the question, how to use the container more safely. Maybe you can drop some Linux capabilities, such as firstly, you can permit or forbid the Docker to do anything. Secondly, you can mount the rootfs as user read-only mode. Thirdly, use the SE Linux or APP Armor to protect container. Fourthly, you can use a safecomp to allow or disallow some system calls. But the more you add, the thicker the middle layer will be. It will cause more performance overhead. So the original Docker, i.e. runC runtime, can't perfectly resolve the security issue of container. It needs a strong isolation level additionally. The Kata Containers runtime is compatible with the OCI runtime spec. Therefore, it works seamlessly and perfectly with the Docker engine. Besides, it also supports the Kubernetes CLI through CLI-O or containerd. In other words, you can transparently select between runC and the Kata runtime. This is the flowchart of Kata Containers architecture design. The Kata agent is a process running inside the guest as a supervisor for managing containers and processes running within those containers. The Kata proxy is a process offering access to the virtual machine Kata agent to both Kata stream and Kata runtime. Besides, the Kata proxy is a process. The main role of the Kata proxy is to route all the I/O stream and signals. It will connect to the Kata agent on a Unix socket, i.e. VSOC. The Kata proxy uses YAML and multiplex gRPC requests on its connections. Another shim process is Kata shim. It will run inside the host environment and handle the standard I/O and signal on behalf of the container process, which is inside the guest. So what's the status on Arm64 for Kata Containers? Firstly, it runs smoothly on Arm64. You can install the Kata container on Arm64 by snap install in several distros. for example, Ubuntu. You can run. You can build it from source code. And for running the Kata container, you can use the CTR command line to pull the image and run the simple test case. In this case, is running a busybox. And you can even run the Kata container on a Raspberry Pi 4 with minor changes. This is the features comparison between ARM and 64. As for hypervisor, Kata let the hypervisor create. It supports the most cases, something like the QEMU, Firecracker, and Cloud Hypervisor are all supported in both x86 and Arm64. But currently, Arm64 doesn't support Acron. The Kata container will let the hypervisor to create the NVDIMM device and then mount it as a guest rootfs with DEX mode. It will speed up the boot time or share the regular files, image files. So NVDIMM device with DEX mode are both supported on ARM and 64 x86. And the Kata will use Virtualization and mount it as the Kata Containers rootfs. Currently, the Virtualization are supported on ARM. The asterisk for QEMU here means the upstream QEMU supported, but we haven't introduced the feature into Kata Containers project. The VM template is an interesting feature I will introduce later. It is to speed up the boot time. And the Rust agent is to rewrite the Kata agent with the Rust language. And the Kata runtime will start a virtual machine with limited resource at the beginning, and then use the hot plug to require more resource. But currently, the memory hot plug is, especially the ACPI-based memory hot plug, is supported in upstream kernel and QEMU, but it needs some time to introduce it into Kata project. The vCPU hot plug patch is under review and upstream review on Arm64. And Arm64 doesn't support next KVM, which is very important for Kata CI subsystem. The Virtualization is a shared file system that lets virtual machines access a directory on the host. Unlike the older approaches, it is designed to offer local file system semantics and performance. It is based on Fuse. The Fuse protocol is not based on the network protocol. It means fast performance and better semantic capabilities of process. There is a independent virtual FSD demo, more safety, and it doesn't need to maintain the block device, the device mapper, compared with the IPFS. And by using the DEX mode, you can improve further improve the performance. You can bypass the guest page cache and avoid necessary VM exit. And the limitation is for the WatchFS is that we once observed that the WatchFS will increase the system memory footprint because the shared pages disallow the KSM to merge the pages. So maybe in the future we can improve it, find some better solution. The internal tests show it. The virtual FFS significantly improves the file system performance in Kata project compared with IPFS. From this chart, by using virtual FFS and the DEX mode, the performance of virtual FIO read-write, the performance data improves about 10 to 20 times. This is the functional features list. What Arm containers teams have done. Firstly, we enable the runtime and the Rust agents for Arm64. We maintain the CI subsystem on Arm64 for Kata. We enable the integrate the Firecracker and not only integrate the cloud hypervisor, but also enabled it on Arm64. And we finished the Kubernetes integration test with Kata Container. There is something to do, need to do in the future, something like the memory hot plug and the vCPU hot plug. The memory hot plug including the virtual I/O mem, which is a feature a trade-off between the ACPI-based way and the virtual I/O memory bloom. Also, we need to verify and improve the next state virtualization if the upstream patches are merged. So let's come to the performance comparison. The performance comparison, we focusing on several aspects, something like the boot time and the binary code size and even the memory footprint, including the virtual memory and the physical resident memory. This is the hardware and the software setup environment information. The host and the guest kernel version and even the QEMU version and also the Kata version. This is the performance comparison for containers boot time. In this case, I once started running a simple Kata Containers test. I mean, enter into the container and run a simple shell command and quit at once. I run this test for 100 times, then calculate the average data for the boot time. And the x-axis is the boot time difference to the starting point. The y-axis is the millisecond time. We watched that the most gap is between the VM started and the agent started, i.e. kernel boot plus VMM boot time. In this case, is QMU. I should mention that the boot time might be a little different between different configurations. The total boot time of the guest kernel is not too long, but we still found something to optimize. We reduce the kernel boot time from more than 100 milliseconds to 80 milliseconds. Another tunable point is the systemd service, but given that most of the distro enable D, so we didn't remove it as what Alpine did. From this chart, we conclude that the boot time gap on Arm64 compared with x86 is not the guest kernel's boot time. This is the tuning items what we have done for the boot time. For example, we disable the PMU initialization because it will take about 20 to 30 milliseconds. And we set the SCSI scan mode from synchronization mode to none mode. And we disable the Virtual MMIO device initialization because Kata Container will not create any Virtual I/O MMIO device on Arm64. We could consider a more aggressive way to speed up the boot time, something like VM template. The VM template is a Kata Containers feature that enables new virtual machine creation using a cloning technique. When it is enabled, the new virtual machine is created by cloning from a pre-created template. And they will share the same initial RAMFS, the same kernel, and even the same agent memory in read-only mode. It's just like a process fork. But there's something wrong on Arm64. It is expected that the QMU doesn't write anything to guest RAM memory until the VM starts. But it really does in Arm64 QMU. So we fixed this issue and enabled the VM template feature for Kata Container. Actually, Kata will start a simple guest with limited memory or vCPU resource, hence reducing the binary code size is a tuning point. So from this chart, we reduce the binary size of Kata service. I mean Kata runtime agent and even the container D shim v2 binary by about 20 to 30%. We also tuned the VMM currently Cumul only by customizing the configuration and even tripping. The binary size was reduced by about 20% with configuration tuning and more 60% with stripping. This is the flowchart to summarize the Cumul virtual memory footprint size in megabyte size. The possible reason why the virtual machine footprint of Cumul on Arm64 is a little bigger than that on x86 is about the firmware device. There are two P-Flash firmware devices on Arm64. They will take about 128 megabytes additionally. The resident memory, i.e. physical memory footprint of Cumul is on Arm64 is as much as or even better than x86. So from this chart, this is the summary of resident memory size comparison between ARM and x86 for Kata Go agent and Go runtime. The size is close or even the same. This is the performance tuning items, what we have done. For example, the VM template support, the VirtualFS and DEX support enablement and bug fixed, and the persistent memory and VDIM support and bug fixed. This is the user stories of Kata Container in Chinese internet giants. Firstly, Baidu, a dominant Chinese search engine operator. Its AI cloud is a complex network with huge amounts of traffic and complicated deployment scenarios. The peak traffic, especially is about 1 billion page views per day and 50,000 containers for a single tenant. Baidu chose to use Kata containers after doing extensively research on secure container technologies and determined that Kata container is a highly secure and practical container technology. Another case is Alibaba. As one of the important founders and maintainers of Kata community, even the Kata project, Alibaba uses Kata containers in its ECS bare metal instance plus Kubernetes as a serverless infrastructure. So that means Kata Containers project becomes more and more hot. So that's all for today's presentation. Thank you.